Welcome to the next lecture. So today we will talk about how to display numbers on a line, which is called the real number line. What is it and why do we need it? Now, what is the number line? Number line is actually, it's a concept that answers the question how to mathematically measure numbers or distance. So let me throw some light on it. Let me give you an example. Suppose you are a school teacher. Suppose you are a teacher and you have 10 students. Suppose you are a teacher and you want to make 10 students of yours stand equidistant to each other. Maybe you just have 10 students in your class and you want them to stand equidistant to each other. Maybe you are following the norm of social distancing and there's a particular distance that you want them to stand from each other. So the situation will be like, how would you place them? The scenario is that I have to place 10 students and here's what I would do if I am you. So I'm going to place 2 students first to begin with. And 1 student is here, 1 student is here, right? Now what I'm going to do, I am going to calculate this distance, this length, make the third person stand at a position which is absolutely same distance as this one, from this person. So what I will do, maybe I use my finger, maybe I use a scale. Since I'm working with some software tool, so I'm going to use just this, and I'm going to mark exactly this amount, this line out here. I'm going to mark exactly this line out here. Now I will be placing the third person out here. And I know that this third person is absolutely equidistant from the second person. So which is what I wanted, which is what I actually wanted, right? This person, again, I want equidistance. So what I'm going to do is I'm going to, again, cut that piece off and exactly the same distance at the same distance, I'll just take that piece of line and I'm going to place the fourth person out here. They are equidistant. And this process can go on and on till the 10th buddy. Okay, so this process can go on. And in this manner, what I've done is I've made sure that they all are standing equidistant to each other. So I'm dealing with positioning here. So without naming them, what I can do is I can say that this is the first person. This is the second person. This is the third kid, and so on and so forth till the 10th one, right? So I have 10 points here on a line. If you may look at it, this is a straight line which has 10 points on it. The notion of number line is also something of that sort. So you have numbers equidistant to each other put up on the number line. So if we call the first position 0, the next position we can call 1. Equidistant to 1 will be the position 2. Equidistant to 2 will be the position 3, and so on and so forth. So we can keep on writing our numbers out here, equidistant to each other. 1 unit distance is what we can see here. I'm starting with 0, so it is whole numbers out here. So the distance that between 0 and 1 is 1. The distance between 1 and 2 is also 1. And if you would want to measure the distance between 0 and 2, it is the 0 and distance between 0 and 1 plus the distance between 1 and 2, that would give you 2. And so on and so forth. So 2 numbers are differing from each other just by 1 unit, 1 number. So that means the distance between each of them is actually 1, 1, 1. Okay. So that's how you display numbers, the whole numbers on a number line. This is what is a number line. The number line doesn't stop itself to just the whole numbers. You can extend the number line to whatever kind of numbers that you have, that we have learned about in our previous video. So all the real numbers could be represented on the number line, and that's what we will learn right now. Why am I focusing on this equidistant property? That is because you can make use of number line according to your requirement. So in case I want to analyze numbers only between 90 to 100, I am probably marking my 10 students out of 100, and I want to just mention who's got marks from 90 to 100, different marks from 90 to 100. So what I can do is I can start my number line at 90. I do not need to write all numbers from 0 to 100. I can just write down, I can just have my number line starting from 90, moving till 100. But yes, when you are quoting 91, if you want one natural number up on the number line, they all have to be equidistant. They all have to be equidistant. So the distance between 90 and 91, the same distance should be portrayed between 91 and 92. Then comes 93, 94, 94, 95, 96, 97, 98, 99, and 100. Okay? They all have to be equidistant. They all have to be equidistant for it to be a number line. And that's how you will be able to analyze it. So in number line, what you have to keep into account is that you can display whole numbers, natural numbers. We've just done that. But again, as I'm able to, in fact, denote numbers from 90 to 100 for my analysis, I should be able to denote numbers, display numbers, all sort of numbers, even the negative numbers. I can display negative numbers as well. Again, the whole point should be that all these numbers are equidistant from each other. All these numbers are every next number. So the distance between 0, 1 is same as the distance between -1 and 0, so on and so forth. So that's what is an extremely important property that you have to concentrate on. So I can display integers as well. So we've spoken about whole numbers being displayed. We've spoken about natural numbers being displayed. Now we are talking about Z, that is a set of integers. You can display them. All the integers, they go on and on and on. What you would realize, whether it is whole numbers, natural numbers, or integers, what you should realize out here is that towards the right that you go, the numbers are increasing. Towards the left that you go, the numbers would be decreasing, be it this number line, this number line, this number line. So towards the right, the numbers will be increasing. Towards the left, the numbers would be decreasing. It's very easy to see in integers, especially. So 0, if we take the center of our line as 0, so you have all negatives here and all positives here. You have all negatives here and all positives here. But this is not the only thing. What I am trying to tell you here is that the numbers are in increasing order here. So every next number is bigger than the previous number. And because the length from 0 of that number is more, so the value becomes higher. And so it's increasing this side and it is decreasing this side. So even if I start from here, it is decreasing this side. Okay, 0 is lesser than 1, 1 is lesser than 2, and so on and so forth. Okay, so that's an important thing that you should always keep in your mind. Now, we have spoken about integers as well. What about rationals? What about rationals? I know that whole numbers, natural numbers, integers, they're all rationals. But what about fractions? Can I display fractions on the number line? Can we display display fractions on this line? And the answer is yes, absolutely yes, we can do that. Because the concept of equidistant, we can actually try that out with fractions as well. So let me give you an example here. So suppose we have 0 here, 1 here, 2 here, 3 here, 4 here, and so on and so forth. So I'm not writing down more numbers out here. Suppose we have these numbers here, and suppose I want to talk about fractions. I want to display fractions. The easiest to think and start, let me just talk about half, the number half. Where would half be located? What is the location for half? Half means it is half the distance from 0 and half the distance from 1. So it will be absolutely in the middle of 0 and 1. But now I want to talk about 3 by 2. 3 by 2. So half, which is 0.5, is located here. 3 by 2 is 1.5. So clearly it is half more than 1. So what I can think, 1.5 is half more than 1. So it's going to be half unit more than 1. So it should be located here. It should be located here. So it is half unit prior to 2 and half unit beyond 1. So it should be located here. So what have we done? We have located 0.5, we have located 1.5, and so on and so forth. We can keep on going, right? We can keep on. Now let me just highlight this part. So let me just highlight this part. So this is what we have. This is what we have, okay? This is what we have. So half is here, 1 is here, 1.5 is here. Now 1.5 is actually 3 out of 2. 3 out of 2. You are displaying the fraction 3 out of 2. So what essentially is happening? So if I take this as 1 unit, this distance as 1 unit, just this amount, I take this distance as its equal amount, so it makes it 2 units. If now, instead of thinking in terms of 0, 1, you take that this is 1 unit and this is 1 unit. So this is in total 2 units. So this position in that sense would become 2 out of 2 units. If I just say that this is 1 unit, this is another unit. So this point will give you 2 units, and this position is 2 out of 2 units. 2 out of 2 units. This position is actually 2 out of 2 units, and that's why the number that you have here is 1. Now I want to display 3 by 2. How do I display 3 by 2? I will go exactly this amount as a unit here, and this is my third unit. This is another 1 unit, and this is your third unit. And out of the 2 units, so this is the ratio. This is the ratio 3 by 2. 3 units where every distance was this. So this is your 2 units. So 3 out of 2 units. This is how you can visualize fraction. Let me throw some more light into it now. The units that I'm talking about. So this time what I'm going to do is, instead of the entire number line, I will just take 0 to 1. Or say I will just take 0 to 10. Let's take 0 to 10. Again, let's take 0 to 10. And I'm going to convert it to 0 to 1. Let's see how. Now what I'm going to do, I'm going to imagine that 10 is actually not 10, but it is 1. It is 1. How I can do that? If I divide 10 by 10, this becomes 1. If this is 1, then that means this is every single distance that you see is 1/10 part, because what I'm saying is that this position is 10 out of 10 parts. I'm saying that this position is 10 out of 10 parts. That means what I have is, I have 10 parts. I have segmented this line in 10 equal parts. I have segmented this line in 10 equal parts, and this is 10 by 10, all 10 parts by 10. That is, this is entire thing is 1. And if I look at this point is showcasing 9 parts out of 10. That means we have moved from the first position, 9 positions out of total 10 positions. This is 8 by 10. This is 7 by 10. This is 6 by 10, 5 by 10, 4 by 10, 3 by 10, 2 by 10, 1 by 10. Now, if you look at this, it's nothing but you are displaying 0 to 1. You are displaying 0 to 1. And these are the points in between 0 to 1. So it's really interesting, okay, how you can see there are infinite rationals in between just two whole numbers 0 and 1. I've just mentioned 10 parts right now, but we can pick every part and we can make it another 10 parts. We can cut it in another 10 parts and get further ratios, get further smaller ratios, further smaller decimals. So what I have here is 0.1, 0.2, 0.3, 0.4, so on and so forth. What now I'm going to do is I'm going to just pick this one. Suppose we just take this highlighted part that is from 0 to 0.1, and I imagine that this 0.1 is basically 0 to 1. So now what is happening? I'm again creating, I'm dividing from 0 to 0.1 in 10 parts. I'm dividing the length from 0 to 0.1 in 10 parts. If I'm doing so, that means the next point to 0 is 1/10, because it's the first point after 0. So it becomes 1/10 of 0.1. So that means it's 0.1 upon 10. Then you add 1/10 more. If you add 1/10 more, what's going to happen? If you add 1/10 more, it's going to be 0.2 by 10, and so on and so forth. So what is happening is that from 0 to 0.1, just this fraction part, okay, just this fraction part that you have divided it. You have divided the points in between 0 to 0.1. You've divided it in 10 parts, 10 equal parts. So you have 0.01, 0.02, then 0.03, 0.04, and so on and so forth. That will make it 0.1. The fun part is you can keep on repeating this process. You can keep on repeating this process. You can just take this much part, then divide it into 10 equal parts. Then you can again take that mini part and then divide it into 10 equal parts, and so on and so forth. Nobody's stopping you. So that is why every interval, for example, just the interval 0, 1, just the interval 0, 1, or let me not quote intervals right now. We haven't spoken about them. So any two number that you take, any two whole numbers that you take, you can have infinite fractions in between. Infinite fractions in between, because you can create infinite fractions in between. Okay? And that is why you have, in totality, if you will see, you have infinite rational numbers. But what is infinity? I'm going to leave it for another video. Right now, I would like to display something else on this line. So what we've done is we've just understood that yes, rationals could be displayed on the number line, and how we can display many rational numbers. We don't know what infinity is, but we can keep on repeating the process. Now, can irrationals be displayed on this line? It's a very important question. Can irrationals be displayed on this line? How would I display this kind of a decimal number? So let's understand how we can do that. if say we have, this is our line. This is our line, say this is our line, and I'm going to start with 0 here. So suppose this is starting with 0 here. And this is 1 unit. This is 1 unit. I'm going to keep equidistant from here till here. It's 2 out here. And equidistant would be 3. So it depends on you what kind of a line you want to prepare for yourself. You want bigger distances, you want smaller distances. The distance should be equal, okay, to understand the number line properly. Now, if I pick from this point 1 and I take exactly this distance up here in the space, almost this is exactly equal. So I'm going to call this also 1 unit, 1 unit up. And then I join this point and this point. So I get an isosceles triangle, an isosceles right angle triangle out here. And by Pythagoras theorem, I know that this will give me the hypotenuse as √2. The hypotenuse is √2. In this diagram, what is it telling? It is telling me that this length that you see from here till here, this length is √2. If this length is √2, ideally you should be using a compass for this. You measure this length. You measure this length up here, and then just take the compass to mark a point here, which is exactly this length. And that would be somewhere, marked out here. And that means this length and this length is equal. Or in simple words, even if you're not using a compass, you just use any vertical, anything where you can mark, okay, this is the length, and take that length to the horizontal frame here and mark the point. And that point will be √2, because that's the length that you have here. So the fun part is that it's the same way I can find out √3, I can find out √2, root 4, which is 2 only. I can find out √5, so on and so forth. So for that matter, if you want to understand what is √3, if in the same manner I create another triangle, taking the base as √2, taking the base as up till √2, and height as 1 only. Height as 1 only, okay? It doesn't need to be an isosceles triangle every time. For 1 it was, but it's a right angle triangle for which I can find out the hypotenuse. For which I can find out the hypotenuse. I can find the hypotenuse. So I can clearly see that √3, it's √2 square, which will give me 2 plus 1 square. You will get 3 inside the square root, which means it is √3. So which essentially means that this length that you have here, the hypotenuse that you have here, this length is √3. So you can again check what it is and put it up horizontally. And that will give you √3. For geometrically doing this, we use a compass to do that. Otherwise, we just have to basically know this length and we can mark it here. It's going to be something lesser than 2. When it would be √4, imagine what is happening. What is happening is that you are picking up from here √3, height 1, and hypotenuse would become √3 square, that is 3 plus 1 square, and that's √4, which is 2. So when you will mark from here, you will see that this length is nothing but 2. This length is nothing but. That's how you keep on working, and you can, that means, display irrationals. √2, √3, √5, they are all irrational numbers, and even they can be displayed on the number line. So this case, we have learned that yes, we can display irrationals on the number line. All we are trying to depict here is that all kind of real numbers can be represented on a line. The basis of a number line is how you are displaying the numbers which are equidistant from each other. And then the representations, the different representations around it. Thank you.